So can we start now? Yes. Okay. All right, so let's start. So the topic today for me is something a bit less travel, I guess, which is debugging a build. I don't know if some of you ever wish you could do like GDB make something. Probably doesn't work. And even if it worked just for make, builds are usually a bit more complicated than just running make. So quick thing about me, I'm on a mission to make it easy to reuse free and libre and open source software. I maintain or contribute to many projects. I've been an health helper a bit at some time on strace, contribute a bit on the Linux kernel, mostly to bug people about licensing issues. I'm a co-founder of FSPDX. I used to be a committer on Eclipse and JBoss in the past. Most of what I code in is either Python, C++, and I try to stay away from JavaScript, but I'm forced into it now and then. So why should you care about understanding your build? There's several reasons. First and foremost is you want to have a fine-grained understanding of what gets in your binary. And you would say, well, of course I know, that's my code. I know exactly what gets built. And it holds up pretty much until you have more than one C and header file. Now think about something like building a full Android device. That means a whole stack from the kernel up. This build typically involves multiple language compilers, some pre-built binaries, scripts. There's about 400,000 steps which are executed when you build an Android device, roughly. So that gives you a bit of an idea of the complexity of the problem. And at that scale, this is no longer fully deterministic. Now, even if you don't do system programming, but do application level programming, you create a node package talking about JavaScript, and you say npm install, and well, guess what? You have now 200 or 300 dependencies that were installed from left and right. And at some level, large builds are a bit like magic. We know they work. Eventually they do. Most of the time they do, but it's really hard to understand exactly what happens. Especially like in this case of NPM or Maven or application and language-specific package managers, things are fetched and provisioned at build time, so they come from the network. I remember a long time ago, actually a small JavaScript package, Java package called Rhino, which was a JavaScript interpreter written in Java. And part of its build script was actually doing a wget to fetch some code, integrate it in the build, delete the source, and basically you ended up with some binaries you had no idea where they were coming from. Eventually they were just popping up out of thin air unless you could trace exactly what was happening. There's other applications which is eventually we are all redistributing vulnerable code. We're integrating vulnerable package. There may be licensing issues where things like linking dynamically versus statically when it comes to the LGPL, GPL have their own importance. And this is the kind of things that you want to, which are reasons why you may want to care. So now, let me state the problem is, given some binary or package, I want to know where they're coming from, and eventually which known open source package they're built from. I want also to trace exactly what's the complete corresponding source code, which is more of a legalist term that applies to the GPL. And I want to do that eventually in the large, for large complex build like whole device, or in the small, which is I'm targeting single binaries and I need to understand exactly what gets into it. Does that make sense so far? Is it something that a problem that you guys have had at times? More or less? Okay. It's at some level it's a pretty narrow use case. Most of the time we hope the build runs and we don't have problem with the builds and we don't want to touch it. Okay, so now the techniques to get there. There's many ways. but the only technique I will talk today about is what I call dynamic forward build tracing. That means you have to run the build, and you execute your build with some tracing magic, we'll come to it in a second, such that you eventually can create from this trace a graph of your processes, executables, and file transformation at full depth and full complexity that you can then query to understand, well, here is this source, which binary is it used in? Or here is this binary, which are the source that were used to actually make the binary. There's many other techniques, and they're off topic, but let me cite them just so we can put them out. Anything that would be instrumenting the build tools or the compilers, off limit. The techniques I'm talking here are not requiring any change whatsoever to your build environment. Actually, it doesn't care about what build environment. You could use make, cmake, build a node package, run some script, it doesn't matter. Anything that's static analysis, that means you start from the binary, for instance, collect dwarf debug symbols, which is a technique used by GDB to point back to source, it's out of it. Anything would be tracing the runtime execution itself also. We're strictly talking about the build, though eventually the same tool could have applications for dynamic tracing of runtime execution of code. That's not its primary purpose. Other things, especially disassembly emulation, reusing compiler convention, for instance, a .class file in Java typically comes from the corresponding .java file with the same path or same subpath. So none of that. Symbols and debug symbols also are out of the scope. Actually, the technique here doesn't care about symbols and debugging symbols at all. Now, these techniques are interesting, especially the last few ones are something I'm working on. I said in my abstract that I was actually presenting that too at the end, but I'll come to that in a second. So the problem, static analysis is not an exact science, it's difficult. Instrumentation is, for instance, if you were to instrument GCC or make, there's been several attempts, there's new attempts in that space, is complicated because you eventually have to instrument each and every build. It's very dependent on the internals of the code most of the time. So both dynamic and static analysis are complicated. Static analysis, in the best case, you would have all the symbols that exist in the binaries that you can trace unambiguously to your source, but that's not the case at scale in practice. And also builds, when they're large enough, they're complicated. And there's few people in a team that usually understand them, and few people that are able to make sense of them in a way that they can evolve them efficiently. So just saying, oh, if you mind just making sure that you could GCC compile -g everything, it's usually not trivial. And you turn it in one place, but happens that there's this other executable that's built in another way, and it won't be built in debug mode. So it's in practice, I found it extremely difficult to obtain proper debug artifact where you could do only a static analysis to trace things back. The other thing is that it's pretty hard to conclude that something is not built. So you have a bunch of code, check out. Let's assume you have everything and you're not fetching anything remotely over the network. How do you know which part of the code is not built? It's not completely evident. The other thing that's important to keep in mind is that building is not the same as deploying. You may, for instance, as part of the build, executing tests, and these tests may not be part of your actual deployed runtime binaries. The same apply with tools, and in some case, bits of the tool chain end up in your deployment, but some others don't. So, any question? The context is clear for everyone so far? Okay. So the ideal solution should be very easy on us, requiring absolutely no change to the build and configuration. It should be 100% accurate and allow me to really understand everything about the build. And so what's the approach? syscalls. I'm assuming a lot of you are understanding what a syscall is, but for those that don't, a simple way to think about system calls is that's the machine language of the kernel. The Linux kernel in particular, kernels in general. And the kernel typically doesn't know much about what's happening above. It knows about file system, network, CPU, scheduling, and simple thing it does, it's being asked to open a file, close a file, read some bytes, write some bytes, spawn a process, that kind of thing. So very low level. And that's why it's a good idea to think about it in terms of the equivalent of machine language for user space. Now the other thing about system calls, at least in the context of Linux, is that everything you do in user space ends up as a system call in the kernel. It's 100% accurate. So you know everything that happens, but you're looking from below. The only thing you see is open file, read bytes, close file, these kind of operations, very low level, but you see everything. So the tool, it's called tracecode, and the approach is fairly simple. You run your build under a trace, which is a tool that you have the maintainer in this room, Mitri. I'm not worthy. And strace is a system called tracer for Linux. And the way you run it is that you prefix the command that you want to execute with a trace, eventually some extra flags, and it will collect a trace of everything that happens in the kernel. So it's basically like a disassembly of the machine language of the kernel that you get for whatever you started in user space. In my case, and it's probably not the best case, I'm tracing every system call, which is huge. Like, think about the full stack Android build, 400,000 operations. You're talking about a trace that's in the range of 20 gigabytes. So typically bigger than the executables you're building, and probably bigger than every artifacts and intermediate temp files of the build that were created. And that probably could be optimized, but it's actually simpler just to trace everything. Once you have this trace, we process the trace and we rebuild a directed graph of file transformations that happen over a given tool executable. So again, the system call levels, read, write, open, close socket, file descriptors. And these happen in the context of a process. The process is the context of an executable. And you're basically saying, okay, I have a process. There's some file operations that take place there, so I collect them here. And you trace the life cycle of the files over the processes and executables. Once you have that in a graph model, you can create whichever way you want. You say, okay, I do a topological sort, and from that source file, tell me what is the last file in my graph that's never been read anymore. It's only been written to. It's not read. And what happens automatically in some of the simplest case is that the thing that's only written to and never read, it's at the end of the graph, is actually your binary. On the other hand, if you take some binary and say, give me some file at the end of the graph the other way, going in the reverse way, that's only read and never written, that in most cases is a source file. So the cool thing about that, it's completely agnostic with regards to the compiler, the make tools you use, the build chain. It doesn't care, the programming language, and it doesn't require any change to your build process. And that's really what makes it useful in fairly large array of use case. The only thing you need is to run your build under a trace and run it on Linux. There are ways to collect the same kind of system trace on Mac with dtrace and with some magical invocation on Windows, but that's none of my interest. So but I know it's possible. I've even seen implementations from some testing tool using Chromium that actually has a similar approach. And they're trying to isolate the runs of tests, so they know exactly which files are used to run a single unit test, so they can parallelize that more efficiently. And they use a similar technique to collect, during a test run, which files are being touched. And they've implemented also a dtrace tracer and a Windows-based tracer. And the cool thing is that it really provides this 2020 vision into the build process, at least some aspect of the build process, which is what tools were used, what executables were spawned, what files were read and written to, and in which order. So let's look a bit at the fun stuff. It's a graph, so you can pass it to dot and graph viz, and you can actually build cool things about it. I'm gonna try something very simple first, which is something called patch elf. It's a single C file mini tool created for a distro called Nix, which just fiddles with the elf format internals to do some relocation and things like that. And this is an example of a build graph from patch elf. So let's walk through that. We won't walk through more complex ones afterwards, but let's walk through this one. So at the top, I see here collect2, some executable from GCC 4.6 with some PID at some timestamp. That's what this box says. It actually reads 2 temp files. I don't know why, but it does. I don't know who created these temp files, and this is a dead end in terms of graph. It doesn't go anywhere else, so I can ignore that. Now, more interestingly, I can see my make file that's being read by make. It kind of makes sense, right? That's what the kind of things we would expect, of course. But here at that stage, maybe it's a filtered graph actually in this case, I don't remember exactly. But this doesn't go anywhere else. We see also that bash was running under the control, well, make was running in shell mode, so under the control of bash. So this is a small branch of the dead graph. Here we see another interesting things where there's a .deps directory with .po files together with a make file, which are read again by make. There's some invocation of G++, no idea what it's for. Maybe they're doing some configuratory. This graph has been a bit filtered, and we'll come back to the filtering afterwards. Now, the interesting stuff. Here, actually, let me use that pointer after all. First step, we're reading a .elf file. Then I'm reading my patchelf.cc. A few standard includes provided by the toolchain. And eventually, this is all processed by a tool called CC1+, which, frankly, until I used trace code, I had no idea GCC was actually not some kind of monolithic stuff, but many tools. This is the C++ preprocessor that transforms C code in assembly. It also creates as a side effect some patchelf TPO file, which is some internal file, whatever it is. On the bottom branch here, it invokes the GNU assembler, which eventually produces a .o object file. And finally invoke the linker, LD, to produce, eventually, my patchelf executable. So it's actually pretty surprising when you see the complexity and the number of steps things are going through for a single CC file with one include. There's other stuff that are going at the top, which is eventually dead branch ending in make, processing some dependency files. So there's a lot of these PO, temp, and dependency files which are created at various places during a typical GNU toolchain build. So now, as I said, if I say, patch shelf, tell me what are the source? Well, if you create a graph backwards, the source are this, which are the things which are at the left end of a topological sort, which have only been read and never been written to. Now, if we do a bit more complex things.
Did you filter out all the system libraries which are getting linked, or is it really an example with no .o files from the compiler, no libc, no nothing?
I've probably filtered some of it. So some of the options. Yeah.
You depend on the libc and things like that.
Yeah. In this case, I probably. Go ahead.
Is there a dependency on the makefile? Dependency of the binary file executable on the makefile. There must be.
In some case, that usually depends. But so there's a bunch of options to do filtering, and one of the things you don't care too much about, in many cases, would be to filter out makefiles from your graph. If you're concerned about the source file, if you're concerned only about the makefile, you want to keep that. So this is actually a build from Bash. So that starts to be a bit more complicated, to the point where it's exceeding the capacity of some of my Linux distro PDF viewer.
How do you generate this graph?
So how you generate this graph is you have one option called graphic, a subcommand in traceroute command. Once you've done your processing, you basically say, here are my traces, build me a graph.
Is there only one kind of edge in the graph, or are there two different kinds? Because you have an edge where the process takes one file and produces a different file, but also then you have edges in the graph where you have a process that creates child processes.
Yeah.
And that's why you have these isolated fragments.
So
You have make.
the thing is that we trace process and their subprocesses, we create process tree, and the process tree gets eventually squashed if there's no interesting operation that takes place at an ancestor. So that's why in the graph of if I was looking at the graph of patch shelf, here we conflate, for instance, the fact there's bash and MV in one process. This is actually the child process, and it conflates the executable from the parent process, which didn't do anything interesting, just spawn a subprocess.
How would pipes be shown in your graph?
Excuse me?
How would pipes be shown in your graph? I mean, one program passing data to another program, but never going over files.
Well, that's interesting because I've stumbled on some builds. I thought that early on, GCC, for instance, was always piping, for instance, CC files and CC1 plus files to assembly. But that's not the case. I found actually builds where effectively you had no .s files being created at all. They were just piped. Whatever magic configuration was used, I don't know, but it's possible.
No, I mean, you have one process that gets in the file, it outputs to the character device, the next one reads from the character device.
Yeah, well, you still have socket operations in this case. You still have, file descriptor operations that take place. Even when you're just piping, you still have file descriptors. And actually, we're not really tracing files, but we're tracing file descriptors. So therefore, there are probably edge cases where this doesn't hold 100%, but in practice, and that's some of the things I'll come back to, it's actually a bit hard at times to reverse engineer what happens at the descriptor level, try to making sense of what this means from a user space perspective. There's not always a kind of a 100% one-to-one matching. Another case that's interesting is, say you have a compiler that you can pipe files to, but these files are completely unrelated. Each will be built to something which is completely related to the previous one. That's a use case that happens to, and the trick here which is not 100% implemented, is to track the life cycle of file descriptors and to demultiplex when a given executable looks like it's processing several files that are related, or it's processing several files to write several outputs that are completely unrelated. There's quirks, of course. It's not perfect in all respects, but there's ways to handle these. So Bash, you see on the left, that starts to be a bit messy. Interesting thing, by the way, also you see in the graph, if you have a configure that's executed at some point of time, you'll see a config.h, and you see how and where and when it's used. If we were to look here, actually, I probably have a better. I think Ocular is able to better zoom on these large. Yes, much better. So that's another build. That's cups. It will render eventually. So you see how files on the left, a bunch of C and .h, ends up being multiplexed through multiple processes. As a side note, by the way, in most standard new make build, there's something completely crazy that's going on, which is the presence of RCS files, and a lot of older version control things are checked over and over again. And we're talking like eventually hundreds of thousands or millions and millions of times on a large build, which could represent roughly 10-20% of the time spent in building, just checking for the existence of non-present files. I'm sure there's folks that understand much better make than I do, and there's simple flags to pass to avoid that kind of behavior. But I've seen it in practice on large builds, and it's surprising in some cases how some baggage gets carried over and just impacts every build by default unless you know about it. So in the case of cups, which is a printing tool for Linux, we have a bunch of CC files. We have again assembly that are created, the assembler that's invoked over and over again. Eventually, if we go to the farther right, we have a bunch of .o files. And we have our magic invocations to the linker here, LD. And so in this case, I have something which is probably HPGL, some kind of executable for HPGL printers. I have a shared object created here. And I have some weird loops that may happen. I have a bunch of .a's, static libraries, archives which are created, more executable. So that starts to be a bit more involved. At some scale, eventually, building a graph, unless you have a very large machine, with many CPUs and a very large printer and big screen, doesn't make sense anymore. But it's very handy for reasonably sized, smaller build. Actually, you can even, funnily enough, trace the build of strace under strace. Which has a kind of a nice recursive build to it. And so let's, it needs Ocular too. Yeah, so if we zoom here, we should see a single strace executable that's created. Yeah, it's there on the left, and it's nicely multiplexed in a big LD invocation with a lot of .os. And so it's a pretty straightforward build. Not much to say there. We have some assembly files which are created, which in this case are actually, it's interesting, well, there's always some assembly file that's created, usually in a GCC build at some step. either from the CC pre-processing or the C processing itself, because we don't have C++ yet in strace. Probably not for a long while. All right, so let's go back to the, where were we? We were here. So it was showing some of the output. So it's a command line tool, pretty straightforward. It comes with some help. It's written in Python, primarily. A lot of the heavy lifting is about parsing the trace. There's been some effort in strace to make the trace easier to parse, and eventually that kind of tool could go away in the future, all the trace parsing, but it still requires a bit of work there. And a lot of options and help. The general steps is you run your strace and you want to apply some filtering. For instance, you may not be interested from anything that comes from the toolchain, or some system includes. And then you can do inventories of all the reads and writes, or graphing, or queries of the relationships from a source to a binary, or from any source to any binary. And so the internal model is, at the bottom, there's a bunch of processes which are related together with PIDs. They hold a list of reads and writes, a list of executables that were spawned and forked and their children. And reads and writes are grouped in operations where you have a process that reads some source. Well, we don't know if it's our source code, but reads some source file and writes to some target at some time. There's some specific which are atomic read-write, like a rename, where you have a single system calls that actually reads and writes at the same time, and then the notion of an executable. And the hierarchy then, I've written the hierarchy bottom up, but that's a hierarchy, generally speaking. And then you have relations between each of these. Now the complication, parsing strace, I alluded to it. The thing that's difficult also is tracing the life of a file descriptor, because file descriptors have a number that gets reused. They get a path, and you want to trace the absolute path, but they get reused over time. And right now, in the context I was alluding earlier, which is a long-running executable, which processes a lot of files which are not related, the demultiplexing of this operation is not working great. And what I think about doing is integrating a timeline and tracing for each file descriptor their life cycle in terms of nanoseconds from where they're live to when they're closed. And whenever file descriptor shows up, eventually with the same file path or the same file descriptor number, then it's considered a new one. If it died, it was closed before. So the other thing is anything that jump and non-interesting files. So actually I lied. When I told you it was really completely agnostic, I didn't need to know anything about the build system. That's not entirely true in practice. If you have a large graph, you may have a lot of junk and you want to do some filtering. And this filtering requires to understand what's taking place. So say you don't care about all the .po, .tpo and all these temp files created by make. You may want to filter this. So the facility provided there is to collect inventories of these reads and writes, group them, and then apply filtering command line invocations so you can prune these from your graph. These tend to be fairly repetitive. So say you want to ignore anything in /tmp. And what I'm thinking there to make it more efficient is to build command profiles for typical build environments where there's a set of regex patterns to include or exclude systematically certain files as an option, so that it's simpler to do the simpler things.
Do you only prune to the left, to the source side, or also?
It's a graph, it's a directed graph, so you can query both sides, but it's, excuse me?
Filtering just to one side?
You can, you filter at the process level. So you can say, I want to filter a write that meets this pattern or a read that meets this pattern, or I want to always include a read or a write that meets this pattern. And you can put patterns in a list or just enter a long command line. So one of the original use cases when I built that tool was I was actually doing an analysis of the code base of a large Git repository hoster that I will not name. And there was one problematic executable which was native code, and we didn't know exactly what was the source code that was used to build it. So one of the applications is to understand, for instance, static dynamic linking with other code, especially copyleft code. But another thing is, and it's just one of my side projects is, well, if you know exactly what the source code you have and you're distributing, you know if there's any software package that are vulnerable using it, so that can be an application once you know finally what's the resulting license. If you're combining GPL and non-GPL code in one executable, eventually you can conclude reasonably safely that your resulting binary should be made available under a GPL compatible license. This information of vulnerability and licensing is not always easy to access to on every software packages, and I'm starting a small project on the side with others to help every fourth project maintainers provide more clarity in that domain. So tools, it's on GitHub. It's written in Python, Apache license, and as I said, next step is a few things: file descriptor timeline, separate tool that would work on static analysis and static reversing. So same approach using symbols and debug symbols, which is both more complicated and simpler. In the end, it should fed into the same graph that you should be able to query the same way, or more fuzzy approach using signatures on the binary side. And again, I lied. I said that I would provide also an extension that does the same thing on the static side, but I've not finished it. I started to work on the ELF, Mako, and WinP parsers to extract symbols and debug symbols, but it's still work in progress at this stage. So credits. So strace really works. If you've not used it, you should use it. Use it now. Use it every day. And you'll be really having a happier life because of that. And you can thank Dmitry, who is in the room here, and many other contributors. It's actually one of the longest running, very active open source projects. It predates Linux by a good margin in terms of ancestry. And I didn't invent anything about that. I tried to model something that implemented a paper made by folks much smarter than me, which is a little known paper that I encourage you to read, which didn't come with an open source implementation, unfortunately. These are the guys like Sander Vandenberg, Elko Destra, who are behind the Nix distro, so they know a little bit of a few things about Linux in general. And that's it. Thank you very much. So I think we have 1 minute for questions, maybe 2. 10 minutes. Oh, we have 10 minutes, so that's great. Yes.
So, what is the slowdown? You run everything.
It's from experience about 20%, so it's very acceptable. One of the largest, so some of the largest run I made were on full stack Android device, and using a beefy desktop, IBM desktop with 4 quad cores, each with dual threads, so that was 32 threads with minus J32. The build was taking an hour and 20 minutes as opposed to maybe 45 to an hour. So it's really acceptable. In practice, because you don't always need to dive at that level of detail, hopefully, in your build, the time when you want to do that kind of deep diving, it's not deterrent. Now, do you want to run all your builds on the strace? Probably not.
So, and how big are the trace files?
So the question is, how big are the trace files? Big.
Yeah.
Fucking big. The point is that strace is trying to capture in something that makes sense for human and it's eventually parsable, everything that happens at the kernel level. And if you trace everything, you know, there's a lot of weird stuff that happens in the kernel. Like calling Intel home to make sure everything's fine with Meldon and Spectre and other stuff.
No, but then it isn't practical for distro to run everything.
Is it practical?
For distro to run all their builds.
So is it practical for distro to run all their build on? I guess though, yes, on the ad hoc basis, not on a regular basis. And another question that's related, for instance, is would there be any application for reproducible builds, which is an interesting topic, and that it has some because it helps you get a finer understanding of what's happening. But the difficulty is that because I lied, it's not 100% build agnostic. You need to understand a bit about what's cooking in terms of the lower level file interactions to make full use of it. So yes and no. Yes?
Collapse the calls to the linker over the file.
Can you speak louder, please?
Collapse the calls to the linker. Now I guess you get a node for every call.
Yes.
But if it's called 100 times, it might be useful to just have one node.
So as part of the filtering, you can also filter executable out of your process graph. And when you remove a node this way, what happens is that I rebuild the link between the nodes on both sides. So it's as if, in this case, if you were to prune out the LD executable, it's as if the LD didn't exist and you go straight from CC1 to an executable eventually, which is kind of a bit weird, but that could be eventually happening.
You might still want to see the LD when actually.
Yeah, which is the default. By default, you would see the link process without, it's always there. And you will see as many invocations of the build and the linker calls as there are calls. So if you're building a lot of shared object and executables or kernel modules in the end, you will have a lot of LD invocation. Usually LD is not a big problem in the graph. It's more all the intermediate step of compilation. Yes?
You think this could be a practical approach to detect non-determinism in a build, like when the build calls the system bug or opens a network connection to detect that?
So the question is, could it be used to figure out if a build is non-deterministic, like when it calls a system clock? In its current form? No, because I don't care about anything that doesn't touch a file. Now, the code parses the trace and just ignores things that don't touch files or sockets. You could take the same code and enhance it a bit to trace that kind of things. Yeah, sorry.
You need to finish it.
All right, thank you very much, and I'll be outside if you want to take.
So you have your own network.